So in our previous tutorial, we talked about how PD and HD are somewhat different and tried to explain how PD works by building on your understanding of hemodialysis. Now we're going to talk about the different flows that occur on PD. So what I'm going to draw here Alright, so here we have the peritoneal membrane right here, and here's the patient's belly. And I know it's a crude drawing, but it ought to suffice for the points that I want to make in this lesson. And so we instill PD fluid, or dialysate, into the belly. And when we do that, 4 different processes, all related to each other, are occurring. And so we're going to try to color code these so we understand. Remember that the fluid that you're putting in here has similar concentration of sodium and potassium and bicarbonate as hemodialysis fluid. The biggest difference between the fluid in here, in this belly, and what you use in hemodialysis is the amount of dextrose. And so we're going to label that as purple. So there's dextrose in this abdomen. Now the things that occur in PD are similar to the things that occur in HD. So let me just write this key here, and let's talk about some of the processes that are occurring. So we know that we're going to have diffusion of small solutes from the patient into the peritoneal membrane, and that's because the concentration of the uremic toxins in the dialysate is 0. There's a lot of concentration, a high concentration of uremic toxins in the blood, and so there's diffusion that occurs out into the peritoneal space. We're going to call that diffusive clearance. Now, you have all of this dextrose here, which creates an osmotic gradient, or an osmotic pressure. And you know that there's only 2 ways that fluid can move in the body, either through transmembrane pressure or hydrostatic pressure versus osmotic pressure. And in the case of PD, we're utilizing osmotic pressure, an osmotic pressure gradient, to have fluid come out. And that fluid is going to convect solutes. So as fluid moves out of the body, solutes go with it. And so that's convective clearance. Now, if you've got fluid coming out of the body, you have what's called ultrafiltration occurring. And so that's your third process here, ultrafiltration. And all of this is fine and good, and all of these processes are also occurring in hemodialysis patients. The one difference is that this dextrose eventually will be absorbed back into the body. And that's not something that you see in HD patients. So you have 4 processes occurring when you perform peritoneal dialysis. You have diffusive clearance occurring. You have convective clearance occurring because fluid is moving from the body to the peritoneal space, But when fluid moves across the membrane, you have ultrafiltration. And unique to peritoneal dialysis, not seen in hemo, is absorption of the dextrose into the patient. And so what this creates is a scenario in which you have multiple things occurring, multiple flows occurring at different points of time. So we're going to try to draw that out. Let's see if we can draw this out. Shorten this abdomen a little bit so we get more screen space. And let's make a little graph here. Now this is a simplistic model that I'm going to draw, but it should be sufficient for you to understand the different things that are occurring in PD. I'm just going to clean this up. So we've got 4 flows occurring. All right, let's start at time 0. So here's time increasing in this direction, and here's rate increasing in this direction. And here's our 0 marker right there. All right. So what happens when we instill fluid into the patient at that point right there? So let's talk about the different things that are occurring. We'll start with absorption first. The fluid, or the dextrose, hasn't had enough time to be absorbed. So the rate at which fluid is absorbed is minimal. Now let's go to ultrafiltration. We just started our peritoneal dialysis, but we've already created a tremendous osmotic difference. There's a tremendously high osmotic pressure gradient here, enticing fluid to come out. So we will already see quite a bit of fluid coming out. Because we have a good amount of ultrafiltration, solutes are also going to come out at a fast rate, and that's through convective clearance. Now, diffusion probably had its best chance of occurring somewhere around time 0. Diffusion is going to be occurring, but not at such a high rate, because if you remember, diffusion takes into account the changes in the concentration between a membrane. And the change in concentration is rapidly diminishing across this membrane because of convection. So although you have some diffusion, it's not very high. Now let's move along to another point in time. Farther down, what happens to all 4 of these processes? Well, now you have more dextrose being absorbed because you've given the body more time to absorb it. So it's greater than before. What's happening to ultrafiltration? This is probably where we're getting the maximum amount of ultrafiltration, because we still have not reached our maximum amount of dextrose absorption. We can still ultrafiltrate pretty well. Since we can ultrafiltrate pretty well, we also can convect just as well. And of course, diffusive clearance has now the least opportunity to work, because we have so much convection that the concentration gradients here are not favorable for diffusion. So we got a little blip right there. Moving along, now we're here. So what happens at this time period farther down? Well, now we're going to have an increasing amount of dextrose absorption. And because we absorb more and more dextrose from time 0 onwards, our ultrafiltration rate is going to drop. As a result, our convective clearance will also drop. And finally, we'll get a little bit of diffusion, but not too much. And what finally happens at this time point here? Well, now we have maximum amount of dextrose absorption, and we're having diminishing amounts of convective clearance and ultrafiltration. And we probably have no diffusion whatsoever, but I'm just going to put a little nubbin right there. So let's go over this graph. We have dextrose absorption in purple, and what we notice is that it starts off low and progressively rises. We have ultrafiltration and convective clearance in yellow and orange respectively, and we notice that whatever happens, they seem to go hand in hand with each other. We have a lot of ultrafiltration and a lot of convective clearance in terms of the rate when we start out, and as we progress. We reach a certain point where we then start tapering off, and we start that tapering off when the amount of dextrose starts to be reabsorbed at a very high rate. And then finally we have diffusive clearance, which has its greatest rate probably near time 0, because there's no concentration of solutes in the peritoneal space, but decreases over time rather rapidly. And so this is a generalized estimated graph of what happens to a patient when they're conducting peritoneal dialysis. Now, the only question that's left to answer, at least at this level, is what are these time designations? These time designations are going to play a very important role in determining what type of peritoneal dialysis can be effectively done on a patient. Because if the duration of time to reach the maximum amount of convective clearance is very short, we're going to have to alter the way we do PD. And if that time is very long, we'll also have to alter the way we do PD. So we're going to talk about that in the next lesson. That's called the Peritoneal Equilibration Test, the PET. And the PET is going to fill in the blanks here, these time marks. It's going to help us determine how well or poorly dialysis will be done in a patient. Thank you very much.